molecules like this, and they're interacting with each other, what kinds of interactions are there? Okay. Would we expect ionic interactions here, guys, between these two molecules? No, right? Ionic means you have to have a full negative and full positive charge. Do we expect hydrogen bonding interactions here? We do, right? We have hydrogen bond donor, right? We have H bonded to an oxygen. And this guy can also be a hydrogen bond acceptor, meaning he has electronegative atom with a negative dipole, right? Every single molecule will have London dispersion forces on it too. But again, they're so weak, we usually don't think too much about them unless there's no other forces to think about. Okay? So, there's London dispersion forces between, ethanol molecules, right? There's a lot of atoms on there, they can interact a little bit with each other. Okay? But these forces are relatively weak if we have something stronger like hydrogen bonding interactions. Right? So these hydrogen bonding interactions are orders of magnitude more strong than these London dispersion forces. Okay? But if we had something like this, right? Like, oh yeah, I guess this guy could be a hydrogen bond donor and acceptor, right? Okay. There's still some hydrogen bonding that happens here, but there's so much of this other stuff with no dipole on it. These guys will make a lot of London dispersion forces interactions with each other, and that contributes a little bit more as the molecule gets bigger and bigger and bigger. All right. Okay. So it's all relative. But London dispersion forces are always there, and they're more important when you don't have anything stronger than them. Okay. So again, intermolecular forces hold molecules together. Okay. The stronger those forces are, the more of those interactions you have, the higher the boiling point's going to be, the higher the melting point's going to be, because when we transition between phases, we have to break up those interactions, right? Okay, dipole-dipole interactions, they can be a little bit stronger, they can be a little bit weaker, right? The bigger the dipole is, the stronger they're going to be, okay? And remember, we give a special name to very strong ones between hydrogen bond donors and acceptors, right? Those get a special name, but there's still dipole-dipole interactions, right? So water, for example, right? Okay. So these guys have really fairly strong hydrogen bonding interactions, and they have a lot of them. Pretty much every single atom in water is involved in either hydrogen bond donating or hydrogen bond accepting. Okay. And because of that, water actually has a fairly high boiling point. 100 degrees doesn't sound like a lot, but it's pretty high. Compared to the molecules that you guys work with in math, like on here. This is fluoroethane. This is used in I don't know if they use this so much anymore, but these use this as as a component of refrigerants, like in your AC or whatever.
Freon.
Right? This has do we expect this to have a higher or lower boiling point than water?
Lower.
Lower, right? Because carbon, fluorine, it does have a dipole. It's not going to be as big as a hydrogen bonding interaction, right? Fluorine's pretty electronegative, but carbon's not quite as far from it, right? So they still have these dipole-dipole interactions, positive dipole on carbon, negative dipole on fluorine. They still interact, but it's going to be weaker, okay? And because of that, this is going to have a much lower boiling point, and this actually boils at minus 40 degrees Celsius, so it won't be a liquid at room temperature. Yeah?
Did you say assume that whatever has an H bond is going to be the highest boiling point?
Hydrogen bonding tends to increase boiling point a fair bit. Yeah. It's not the strongest one. I would say if it's ionic, it's going to be super high. Yeah. Like sodium chloride, right? This ionic interaction is very strong. Okay. Yeah, its melting point is in hundreds and hundreds of degrees. Right? It's in the thousands of degrees if you want to try to boil it. Okay. Into vapor. Okay. So these are very strong interactions. Okay. Potassium benzoate. This is potassium acetate actually. It's another salt, right? It's got another ionic interaction, right? And this guy's melting point is also in the hundreds of degrees. Okay, so ionic interactions are pretty strong and they're hard to break up. Okay. Okay. London dispersion forces, again, we usually think about these more when there's not other stronger interactions around, right? So if I looked at something like propane, right? We know propane is going to be a gas, and it's a gas at room temperature because there's nothing really holding it together with other propanes, right? You have two propanes, I don't have any dipoles, I don't have any ionic interactions, there's nothing really holding them together except for London dispersion forces, which, between these carbons or these hydrogens, right? But these are very weak, right? And because they're so weak, it's really easy to boil this, right? This is gonna boil over minus 40 degrees Celsius. The bigger they get, does it make sense that the bigger the atom is, the bigger the molecule is, the more London dispersion forces they'll have, right? So this is hexane, right? It's twice the size of propane. And this guy's got a boiling point of about 7. Right? So you guys have used this in lab, right? You know it's a liquid at room temperature. Okay. So that's pretty much all we need to know about intermolecular forces. Okay. So they're important for determining melting point, boiling point. When you guys get into biochemistry, or if you've done any like biology at all, like protein-protein interactions, protein-ligand interactions are completely determined by these kinds of forces. Proteins when they fold, DNA when it folds, like it's all these kinds of interactions. So this kind of goes back to your guys' lab. A lot of people were asking like, oh, how am I supposed to extract something from something else using like week 2 lab, whatever it is. What functional group is this, guys? Oh, let me do this one again. Okay. Do we do functional groups?
Not yet.
Do we do functional groups? Oh, shit. Okay, we'll get back to that in a little bit. Functional groups are something that we usually don't talk about too much in class because it's just one of those things you have to memorize. And you should know this for the first exam. So if you go to maybe I'll put it in my other class one. Okay, so I'll post this in just a second. Functional groups are basically patterns of bonds, like a carbon triple bond into a carbon that has a special name. Okay, we'll come back to that in a little bit, guys. If we have time, I'll talk about it. If not, we'll get it at the beginning of the next class. Okay. Okay, so this is what's called an amine. An amine is anytime you have a nitrogen bonded to at least one carbon. Okay? And here we have a nitrogen bonded to 2 carbons. The main thing we have to know about this, and you guys did solubility lab already, right? Is that this week? Okay. This week you'll be working with amines, or you'll be working with an amine, okay? Again, the amine you're going to be working with looks a little bit different. It has like, it's going to be like something like this, okay? But the main point is anytime you have an amine, they can be bases, okay? So, we've used curved arrows at this point pretty much just for resonance, right? But we also use curved arrows to do reactions. And when we do reactions, we're changing sigma bonds, okay? So if you take an amine, which is a base, and you put it with an acid like HCl, the nitrogen can use its lone pair to make a bond to this hydrogen, okay? And we represent it with a curved arrow like this, okay? We'd say like, this nitrogen is gonna take his lone pair, and he's going to use it to form a bond with this hydrogen, okay? Hydrogen can only form one bond at a time, so we break this whole bond, and it's going to go into my chlorine, okay? This is what we're going to be doing for the rest of the year. This is how we represent organic reactions, okay? So if we follow the electrons here, how many lone pairs will nitrogen have after I do this reaction? He won't have any, right? Because he's using up his lone pair to make a bond with this hydrogen. How many bonds are on this chlorine, or how many lone pairs on this chlorine before I do anything, guys, if he's neutral? How many does he like to own? 7. He likes to own 7, so he's neutral here, so he must own 7. So how many lone pairs? 3, right? After I do this reaction, how many lone pairs is he going to have? 4. Yeah? Does that make sense, guys? No? Okay. All right. So if we follow this through, right, the nitrogen will use the lone pair to make a bond with that hydrogen, right? The chlorine will have a negative charge because now he has 4 lone pairs. Okay. This is our first reaction. This is an acid-base reaction. Okay. And I know you guys have done this bunch in Gen Chem, but this is how we represent acid-base reactions happening in LChem. Okay? Okay, this is now a salt, right? Okay. What do we think about the polarity of this guy on the right versus this guy on the left? Which one is more polar? The one on the right, right? Because polar means uneven sharing of electrons, right? If you have a partial charge, that's polar. If you have a full charge, that's super, super polar. Okay? This is in your guys' pre-lab reading, right? Yeah, okay. This is gonna be one of the major things that drives the solubility lab, okay? So, we can agree that this guy's more polar than this guy. You guys read about like dissolves like? Okay, which one is more likely to dissolve in water, the left one or the right one? The right, because he's more polar, right? And water's super polar, right? Okay. So this guy's not very water soluble. Okay. Whereas this guy is water soluble, right? Make a smiley face because I don't want to make it again. Okay. Water soluble, not water soluble. Okay. So one of the things you guys are going to be doing this week is going to be basically saying like, oh, okay, well, is this guy going to dissolve in acid? Is this guy going to dissolve in acidic water? Is he going to dissolve in basic water? Okay. This is the same molecule, right? We're in equilibrium between these two forms. We're going back and forth. Okay. If my water is acidic, right? Which side of the equilibrium am I going to favor? So it's basically, right? If I have a lot H plus and this guy can pick up a proton and look like this. This guy can let go of his proton and go back this way, right? If I'm acidic, do I have a high concentration or a low concentration of protons? High, right? That's important, guys. Okay, if I'm acidic and I have a high concentration of protons, which side of the equilibrium do I favor? Left or right? If I increase the concentration of something on the left side, it always pushes it to the other side of the equilibrium, right? Okay. So under acidic conditions, if I have acidic water, it's going to favor this side, right? So would we expect this compound to dissolve in acidic water? Okay, well under acidic conditions, he's going to look like this, and you know this guy is more polar and more easy to dissolve in water, right? What about if it's in basic water? Which side of the equilibrium do I favor? Left side or right side? Left. Okay, so if I have basic water, this guy's not very polar. He's probably not going to dissolve in basic water, right? But the whole point of this upcoming lab is you can, for certain molecules, you can control how polar they are by changing the pH of your solvent. Okay, this always gives people a lot of trouble. Okay, I'm not sure how much your labs, like we usually don't talk a lot in lab because the expectation is that your chem major is like you should be learning a lot of this stuff. But this gives people trouble so often that I kind of just wanted to touch on it and lecture a little bit. Okay. Are there any questions on this, guys? Yeah, okay. So when we do solubility, the idea is like dissolves like. So polar things like to dissolve other polar things. Okay? So let's just make this more carbons. Okay? So can we agree that carbon-carbon bonds are not very polar? This NH bond is pretty polar, right? But the overall polarity of the molecule is sort of an average of all the bond polarities, right? So this guy's not really non-polar, it's not really polar, it's kind of in the middle, yeah? What about water? When we look at water, can we agree that every single bond in water is very polar? Okay, so water only dissolves things that are really, really polar. Okay, so it might dissolve us a little bit, but the more polar it is, like it has a full formal charge, it's going to dissolve it way better. Okay, so anytime you have a formal charge, just assume it's really polar and water soluble. Are we okay with like how you can favor one side of the equilibrium versus another one based on how acidic or basic we are? Yeah. So anyway, so when you guys do that experiment, this is the kind of core concept behind it, okay? So take home message is amines can be basic. The second one you guys are gonna be doing is benzoic acid, I think. Okay, benzoic acid is acidic. Okay. Acids can let go of hydrogens, yeah? Before I do anything, how many lone pairs on this oxygen, guys? 2. Okay. When this guy acts as an acid, he lets go of a hydrogen. The bond breaks between this oxygen and this hydrogen, and the electrons go to this oxygen. How many lone pairs is the oxygen going to have after this? 3. So what's this charge going to be? Okay. So the only thing you have to know for this lab is that carboxylic acids look like this. They have a carbon double bond to an oxygen with an OH. Carboxylic acids are acids. They can let go of hydrogen.
USD GBP.
When they do that, they wind up with a negative charge, like this. Okay. All right.
Oh my god.
So which side is going to be more water soluble, guys? Left side or right side here?
So stupid.
The right side, yeah? Because he's got formal charge. Formal charge means really polar, okay? This guy not so polar, okay? If I wanted this compound to dissolve in water, which side of the equilibrium do I want to favor? Left side or right side?
Oh my
The
god,
right
I'm in
side.
class right
Do
now.
I favor that with acidic conditions or basic conditions? So if I have acidic conditions, does that mean that I have a lot of proton or a little proton? A lot. Okay, if I increase the amount of this proton, am I going to favor the left side or right side? Yeah, if I have a high concentration of protons, it's going to push me back this way. Right? Is this guy going to dissolve in water? No. Okay. So if I wanted to dissolve in water, what do I need to use? I need to favor this side, or I'm going to
GDP, GDP. I have to go to Euro.
So this guy will dissolve in water under
JPY.
basic conditions. So it depends on what functional group you're doing. But the idea is, if you want something to dissolve in water, you need to make it as polar as possible. And you just need to understand the acid-base chemistry to know if you need acid or base to do that. Does that make sense, guys? You did come across this in your pre-lab reading, right?
Yeah.
Yeah, okay. I know it's not like an easy concept, so I just kind of wanted to clarify a little bit. Are there any questions about this, guys? Yeah.
So you're saying that like if our if the solvent is like too acidic, what we're gonna have to do something to make it more basic?
Yeah, and you'll basically take like your compound and you're like, oh, dissolve it in acid or base, and if it doesn't dissolve, if you change the pH, does that change its solubility?
Well, that, if you were like talking about water and.
Ooh, I'm dead.
I think it's like you dissolve it in like
Oh, man.
HCl and then you add NaOH to it, and
I'm
then
going
vice
to
versa.
Euro.
Yeah. So the 1 mole. So again, the thing that confuses people is they think 1 molar HCl and 1 molar NaOH are different solvents. They're the same solvent. They're both water. It's just acidic water or basic water. What time do you go so guys? Are there any questions about that before we move on? All right. This is like the kind of stuff that this will for sure be on the lab exams.
I'm just making sure everything is right now.
This is how your solubility lab works when you guys design a protocol for your extraction lab. This is how your extraction lab
Just
works.
going out for
It's really
GPY.
simple concept.
Let's do this one.
Okay. All right. Okay. So we can take an amine, for example, right? React that with acid. Okay. We can see that it makes a salt, right? Now we have an ionic pair. Each of these has a higher boiling point, guys. Left side or right side? Right side has a much higher boiling point, right? Okay. This is what we call a base or a free base. So if you have an amine and it hasn't picked up a proton, we usually call it the free base. It's just really common terminology in like drug development. Okay. But when you guys actually buy like when you get prescribed meds or whatever,
167.
most drugs have an amine in them, and almost all the time you're going to get it as a salt. They're just more stable that way.
167.396.
And again, this is in equilibrium, right? So under certain conditions, you can push it this way, under certain conditions, you can push it this way.
Oh, shut the Lord to so.
We are saying most compounds have, or most drugs have a salt in them.
396.
Can we see the salt here? It's an amine, right? It has a positive charge. It's making a salt with the chloride, right? This is the structure of powder cocaine, right? We don't do that 'cause it's really expensive. If we take that, right, and if we add a base to it, we can
JPY already got that one. I gotta get your
hydrogen or the amount of protons in
USD.
there. We can remove that proton, right? People typically
I have
do
like
this
at least
using basic
$39.
right?
It's like
We
it's
get
not good.
right? So
It's
if we
for
pull the
metal
proton
lucid.
off, and now you've made this neutral. Okay? Which one's gonna be more water soluble, guys? Left side, right side? Which one's more polar?
Let's go right now this way.
Right side, right?
Opening balance 224. Let's get
Which
this
side has a
side.
higher boiling point? Left side or right side?
Oh shit. 10% up.
So we agree the right side's ionic, yeah?
10%
that gonna make it harder to
winning
boil
so
or
far.
easier to boil? Really hard to boil, right? It's a very strong intermolecular interaction. It's very hard to get it to
I
boil.
need to get it more.
Okay. Okay. So this is okay, and we talked about
5% loss, not bad. Tell you about that, you have to learn how to do 2 a day, 2% one. Win rate, you're gonna 66%. I'm
This is
trying.
regular cocaine. This is how people make crack cocaine. Crack cocaine is just a free basic regular cocaine.
They gotta be smart making one, you know what I mean?
It acts a lot different.
Just crackheads are smart.
Right? If you try to smoke regular cocaine, you'll burn on your coke, right? Because it has too high of a boiling point, right? But the free base is okay to smoke because it has a much lower boiling point because it doesn't have. It's not okay to smoke.
So funny.
Yeah,
Be
yeah.
like it.
Yeah.
We should make one in class, you know? You know what I mean?
Right? So that more polar, how does that affect your ability to cross the cell membrane? Cell membranes have a very non-polar.
It's too bad right now, but
Drugs tend to get into cells better when they're not super polar.
doing 2 ones, USD, JPY is doing bad,
Less
but
polar, it's going to behave differently.
what can I do? What can I do? I'll just set my limit right here.
If it's more membrane permeable, it's probably going to get into your bloodstream. If it's a much sharper physiological effect, then
It's a lot of things, man. I turned 24. I need updates, man. Let me show you more.
strong pharmacological effect really quickly.
24.
It goes very, really fast, and then you're stabbed, right? And then, so this is how you patients for.
Oh, it's like, let's do this real quick. I just gotta do this.
The behavioral conditions that happen in two forms of the
We gotta do this real quick. We just got to.
If you're on a budget,
Triangle.
right? And anything about boiling point, right? This is gonna have a lower
Today is the
So this has a boiling point.
Thursday. It'll be September 8th, January, February, March, April, May, June, July, August, September.
How would the cocaine react with baking soda? You mix it together and it rounds?
Yeah.
We're getting very, very into this topic, man.
So this is going to be one of the first reactions we're going to learn. It's basically
124.
if you have something with a proton that can act as an acid, so this can be a weak acid. Baking soda is just a weak base.
Okay, I'm just making sure that we get 1, 2, 3, 4, 5, 6, 7.
If you imagine this hydrogen on the top,
Okay.
the electrons from this bond have to go somewhere. Right? And they're gonna
I'm
go to this
basically.
Can we see that? Give that and so now is that at low pair, now he's neutral. So
There's like.
it's just like the amine reactions we were doing earlier.
So you said a week on and
$20 a day.
Yeah, so this guy's a weak acid.
So let's get this going. Let's see how the one doing. You gotta be very optimistic, you know what I mean? You just can't be out here. I'm still losing. You just gotta be patient, bro. That's all about it. And I don't know why. It's just actually falling.
So like when you see like you've ever seen like
If you have any question, you can put it down below.
baking soda, but you're just boiling the free base off of the baking soda.
You can reverse that chemical reaction, can you?
What's that?
You can reverse that.
And you can reverse it, yeah. So if I wanted to turn this, it's like, oh, I'm tired of drinking crap. You just put this with a little bit of acid and send it back that way.
Those people that make crack cocaine, they're smart.
You ever watch like
You know,
videos
right?
of, like people harvesting coke in the jungle and stuff? They're like shaking it up with like water and diesel fuel. All they're doing is they're just changing the pH of those solutions to get the coke out of the plants and they go into the diesel fuel that they can evaporate off later.
Wow.
It's just the same chemistry. Diesel fuel is like non-polar, right? Water's non-polar. Oh, this is wacky. Yeah, so it's because you can have a ring like attached to another ring and they can build these like really weird structures.
Mm.
Yeah, it's just a ring attached to it. Yeah, and a lot of drugs have. We'll talk actually more about that. But
Like,
well, rings are much less flexible and they fit into certain protein receptors in your body a little more readily.
shit, it's just bad right
So a
now.
lot of drugs would be like very rigid like that.
Just to confirm, the.
Baking soda, right?
No. Do you see where the lines intersect, like where the carbons are at? That's
Over here, over here.
next to it, to the left,
This guy's very, very fascinating.
and then to the right. Oh, so that doesn't count as one, right? One in the middle.
This is carbon. Yeah,
No,
this is
the one
carbon,
in
this is
between.
carbon. And these two carbons here attached to this nitrogen up here.
Oh, okay.
So
I thought they didn't like connect at the base there too.
Oh, no. Oh, they don't, this is not a carbon. That's
Oh, okay,
absolutely
okay.
correct. Yeah, it's a weird, we haven't talked about this
Yeah.
yet. That's absolutely right.
March calls by trying to flip this right now.
This is just where it overlaps because it's a three-dimensional shape, but there's not an actual carbon there. Yeah. Don't worry about that too much for now, but anyway, right? Chemistry's coming alive. Okay. You can smoke it, right? Right, so you can't smoke it. This guy, I love how much of like a dirtbag this guy looks like.
like I've heard people do this. They add baking soda because by itself it's more pure, right? There's no way that they took the like chemistry and learned all this. They probably just word of like.
So I mean, you ever see, yeah, I mean like.
They're smart though. Like without being a chemist, dude. Like that's really smart. Like we're making fun of them. We should be learning from them.
A very small amount of, because if you took a very small amount of coke like this guy over here on the right side, like it's a very small amount. It takes a while for you to get in. If you start it up in your nose has like enzymes that will break down certain parts of this molecule. It's not like super efficient, right? But if you turn it to the freebase and you smoke it, you bypass all of that stuff and you just go straight into your lungs.
Ooh.
Also, when you snort stuff or when you eat stuff, it has to pass through your liver first, and your liver does a lot of detoxifying, right? And if you're on a budget, you don't want to pass it through your liver first, right? You just want it to go straight into your bloodstream.
If you're on a budget, it's funny. Crackhead on budgets. Imagine. Is it someone to make heroin, right? Heroin is the same thing, right? Crack and cocaine is the same thing.
So,
14 more minutes.
So make smart choices, guys.
Your chemistry, right? You have the lab.
Recognizing polar bonds.
Do we have to print out anything for this to the lab?
In general, we can think about the polarity of a molecule. It's just, oh, mostly polar bonds are probably polar.
From the
Yeah,
book?
mostly non-polar
The-
bonds are more non-polar. But
this
it's
book?
not exactly that simple, okay? Shape is
Lab
gonna
book?
be a big part
That's
of
all we
it,
need, right?
too.
Yeah, it's all the.
So this is water.
pre-book
Oh,
is
it's
from
polar
the
because all of his bonds are polar.
This one, that's what you need, right? Okay, let's get that.
Right?
I was getting nervous.
You know where the dipoles are at. Okay. If we take something like ether, like this is that diethyl ether, it's a little bit polar, but it's not.
My bad,
quite
guys.
polar
If
as
you have any question, put it down below. If you have any question, put it down below, man. Thank you, guys, man. I'm in class right now. That's the funny part about it all. I'm in class right now, so I'm just like,
You call that slightly polar, right? So usually like when we're
gotta go. So you know, just a cheat code right here, man.
Really not
AUT, high USGB, I already got that.
Okay, so this is why we talk about shape. Okay, so what's the shape of this
Oh, interesting.
oxygen, guys?
That's
Bent.
about
Or technically go for
100% straight it already performance now.
When we think about dipoles, we
See,
think about, like, oh,
it's not
dipole,
bad.
negative dipole, positive dipole. It's more accurate to think about them as having a direction, right? So we can draw them as arrows pointing in the direction
It's
where
taking
the
a long
electrons
time.
are getting pulled.
Stick
Okay.
with my
So they're going to be going towards or away from oxygen, guys? Towards, right? Okay. So So the head of the arrow is going to point towards where the electrons are getting pulled. The base of the arrow is going to start where the electrons are getting pulled from. Okay? This is what's called a vector. A vector is just anything that has a size and a direction, right? So the real polarity of this molecule is just the sum of these arrows. Okay? So if we add this arrow here to this arrow here, does it make sense that they kind of like average out and point in this direction? Yeah? Okay. That's what we call the net dipole. Okay, and that's the more accurate way to think about a molecule's polarity. Right? So if we add these two guys together, I don't know, it's getting cut off like that. I'll fix that later. Right? We can think about those two dipoles as kind of adding up and going in sort of this direction.
Gotta make sure they're all.
Alright. What about this guy here? Are the electrons going towards or away from chlorine? Towards. It's going pretty electronegative, right? So we have the CC bonds not polar, CH bonds are not really polar, but these carbon-chlorine bonds are fairly polar, right? And they're both kind of pulling in these directions, right? If we put these together, does it make sense that they would kind of average out to do something like this?
Let me see what the
Yeah.
preferred
So as long as you,
dipole.
so when we say something has a net dipole, we mean that if you add together all of its little dipoles, then it makes a dipole.
Okay.
Right? And it can, that net dipole can be big or
I'm still
small.
losing right now, man.
That's the more
Still
accurate
losing.
way to think about molecular dipoles. Okay. What if I have? Does this guy have a net dipole? They're going towards the bromine, right? Right. If I add all of these up, can we see that they kind of point down, sort of in this direction, after we average everything out? Okay. What about if we did this? Okay, which way are the arrows going to be pointing, guys? Towards the bromine or the bromine? The boron or the fluorine? Fluorine, yeah. Okay. Okay. These are huge dipoles, right? Fluorine is much more electronegative than boron. What's the shape of this boron right now? What's his hybridization? Let's say that. Does he have a lone pair?
No.
No lone pair, right? So he's sp2. Yeah? He's sp2, he's trigonal planar. Yeah?
So down.
If he's a flat triangle and you have one guy pulling down, one guy pulling up and to the left, one guy pulling up and to the right. You can also imagine it's like if you have, if these are three people, and they're attached by like a rope to some center point. This guy's walking this way. this guy's walking this way, this guy's walking
No,
this way.
still down.
Does it make sense that these would all just kind of cancel each other out? Okay. So even though this molecule has three very polar bonds, if we think about the shape, right? There's sp2, trigonal planar. The net dipole is actually 0 in this case, but we wouldn't understand that unless we knew what its shape was. Okay. So, yeah. So again, a lot of small concepts coming together, right, when we problem solve, right? We have to understand shape, which we have to understand hybridization to figure out. Then we have to be able to recognize dipoles, okay? And then kind of fit that all together and say, like, which phase is net dipole in each one? Okay? So this is kind of a deceptive case here, okay? So even though boron, trifluoride, BF3, right? Even though it has three very polar bonds, the overall net dipole for that molecule is 0 because they all cancel each other out because they're all going opposite direction. Okay. What about CO2? CO2 looks like this. Those are oxygens. Okay. What's the hybridization of that carbon? sp2 or sp? sp, right? Because he only has 2 single bonds. So these sp hybridized, what's the shape? Linear, right? Can we agree the dipoles go this way? Does this guy have a net dipole?
You know,
Yes,
if you have any question, bro, put it down below, man.
This guy,
I'm really trying to flip it. My main goal is trying to make a list, like, I was like,
so
I don't know if we're less than
intermolecular interactions, that
like
covers net dipoles.
213 so far.
Today I want to start a little bit on nomenclature. We have about 8 minutes left. I think that's enough time. Nomenclature again is something that I tend to teach just in
12.
very introductory part, and the rest of it is pretty straightforward. You just have to practice. Okay?
12, this
A
one.
couple of things
I'm
that we
trying to
have
show you guys
to
my plan real
recognize
quick.
before we start doing nomenclature. Okay? sigma bonds, okay? And remember, every single bond you see is a sigma bond, right? Sigma bonds can rotate, but pi bonds do not rotate, okay? So when you guys get your models, you can see like, oh, let's connect two carbons together, I can like twist them around like this, and it's the same molecule, right? Like, even if I take two carbons and I put them together like this, and then I kind of twist this front carbon, here the hydrogen is pointing down, right? Here the hydrogen is pointing up. But we can see that it's the same molecule, right? I just kind of rotated the bonds a little bit, okay? This is called change in conformation. Conformation is just when you rotate bonds, but you don't break bonds, okay? And that's what the next chapters are gonna be about. But for now, just recognize that single bonds can rotate. But anytime you have a pi bond, you don't rotate them. So if I have something like this, right? I have single bonds, I have a pi bond. Hold on, that's not what I want to talk about. So if I had something like this, right? This is all sigma bond, right? Sigma bond with chlorine, sigma bond between two carbons, sigma bond here. Can we recognize this is the same thing, right? All I did, I have a chlorine, carbon, carbon, chlorine, right? Chlorine, carbon, carbon, chlorine. They're the same molecule, I just rotated a bond, okay? So we need to recognize when these are the same or when these are different before we can start naming, okay? If I have this has a single bond, yes, but it also has a pi bond, right? If I have a pi bond, I can't rotate it, okay? So this molecule and this molecule are different, okay? It's a chlorine, carbon, carbon, chlorine, right? But I can't rotate a pi bond.
I'm still at a loss right now.
Okay, so if I have to break a bond to make something look like this guy, they're different molecules. Okay. Okay. So with that in mind, let's talk briefly about how to name molecules. It's really, really straightforward, and once you know how to name one molecule, you can name pretty much everything. Okay. We'll get back to this. When we talk about things that are on, you have things that are attached on the opposite side of the double bond, we call that trans, right? When they're attached to the same side of the double bond, we call that cis. So when they talk about like cis fats, trans fats, that's what they're talking about. Right? It's just how your double bonds are in your fat. Okay. This is in kind of one of these weird intro chapters in your book. It doesn't have its own chapter, it's just kind of a footnote almost, because again, nomenclature is not super complicated, but we do have to talk about how to do it. Okay, so nomenclature is how do we name molecules. Okay. And organic compounds can be very, very structurally complex, right? When we name molecules, we have to talk about we haven't talked so much about functional groups, I'll touch on it more later, but just for now, we're going to be talking about what we call alkanes. Alkanes are just molecules that don't have pi bonds, and that don't have pi bonds. Let's just leave it at that for now, okay? When we name an alkane, okay, the name is based on how many carbons do we have in that molecule, okay? And then we end that name with ANE to indicate that it doesn't have something else on it. It's not an amine or carboxylic acid, it's just carbons, okay? So if you just have one carbon, okay, a carbon with 4 hydrogens on it, we call that methane, okay? It would look like this, CH4. If you have 2 carbons in a row, we would call that ethane, okay? So these prefixes, we'll be using these all year for different molecules, okay? But meth means 1 carbon, eth means 2 carbons, okay? Propane, or prop means 3 carbons, right? So it'd be 3 carbons in a row, right? 4 carbons in a row would be called butane, okay? And you guys just need to memorize the prefixes for everything up until about 10, 12 carbons, okay? So a lot of these also sound like shapes. Like 5 carbons is pentane, like a pentagon. 6 carbons is hexane, like hexagon. Heptane is 7, octagon is a shape. Octane like octagon, nodane, decane. Undecane, dodecane for 11 and 12. So let's just go that far. It goes on for a long time, but you know, it's not a class on memorizing names. So this will get us through most of what we need to do. Okay. So just be responsible for those first 12 chains. Okay. All right. So let's come back to the slide a second. Just trying to make it work with the last 3 minutes that we have. Give me a sec. I'll reorder this, okay. Okay. So, let's just stop. I feel like I'm rushing now. Okay, let's leave it there, guys. On Tuesday, I'll post the slides up so you can work through it too. But we'll go through them together on Tuesday. On Tuesday, we will talk about naming and